Am I started? I'm not started yet. Oh, okay.
It's 9:03.
Oh, okay. All right. So, okay, I will start.
You can always blame the session chair.
Right. Well, now I have an excuse to go on later than. Okay.
3 minutes late at the beginning, that's 20 minutes late at the end.
At least. Was it really 3? I thought it was more like 7. Okay. So, actually, I should start by asking if there are any questions from last time. Okay, so I'll start by reviewing what we ended up at. This was the formula by Ryu and Takiyanagi. And actually, the way that I'm presenting it is a generalization by Hubini, Rangamani, and Takiyanagi. So the original paper considered static geometries and gave a formula for the holographic version of entanglement entropy, and then this paper generalized to gave a proposal for arbitrary time-dependent geometries. And so the idea was that you have some holographic CFT. It's in a state that has some classical geometrical gravity dual description. And then you can consider the entanglement entropy for some region A in the field theory. And the claim is that if you look at this dual geometry and you find a surface which extremizes the action, extremizes the area, such that the boundary of this surface A tilde is the same as the boundary of the region A, that then the area of that extremal area is equal to the entropy times 4g Newton. Okay. And in certain cases, there could possibly be more than one extremal surface, and then you're instructed to choose the one that has the minimal area. Okay. So I think Juan talked about some various pieces of evidence for this, so I won't spend too much time on that. In the cases, so as usual in ADS CFT, there are not a ton of cases where we can directly compute things in the field theory at strong coupling. Cases where you can include the entanglement entropy for a ball-shaped region, or in the case of 1 + 1 dimensional CFTs, in the vacuum state, for 1 + 1 dimensional conformal field theories, you can compute the entanglement entropy for more generally in various other situations. For example, for the thermal state, finite volume. So there's various calculations you can do. So all the ones you can do match. Then there are a bunch of consistency conditions. So there are properties that are obeyed by entanglement entropies that I think Juan talked about, such as the strong subadditivity of entanglement entropy. And if you use this formula, starting from a reasonable geometry, so a geometry which is a solution to Einstein's equation, say sourced by some reasonable energy that doesn't violate, say, the null energy condition, then you find that these various inequalities are satisfied. So it's actually fairly non-trivial. If you violate energy conditions, then you can actually find geometries that for which these quantities don't obey the strong subadditivity inequalities. So I'll probably talk about that a little bit more in the last day. That's a way of trying to use this proposal to actually rule out certain spacetimes as being unphysical. Okay, so energy conditions are usually things that you don't prove, you just assume based on the fact that they sound plausible. But there's an interesting direction where you could, by saying strong subadditivity is absolutely always satisfied in quantum mechanical theories, if you find a geometry where that would be violated, then that really can't be showing up as the dual of a physical state. And then there's been an argument by Maldacena and Lukowitz. I think so far this works for the static situation, but I know that people are trying to generalize that argument to more general situations. So there's some evolving understanding of fairly good understanding of why this should be true.
So actually, I'm curious when you say that thing about the energy conditions.
Yeah.
I forget how they're labeled, but one of them would be violated by a consider space. It violates one of the
Oh, yeah.
I'm curious about whether this thing would rule that out and say that for that reason you can't create in the lab, maybe, or instead is it that you rule out the other energy conditions?
Yeah. So that's right. So it's normally for the strong subadditivity. So far, the evidence is that it's the null energy condition, and actually, it's actually somewhat weaker than the null energy condition. It's some kind of integrated null energy condition. So, but it would be interesting to, it would be interesting to talk a little bit more. But okay, so let me talk about some implications of this. Okay, so this formula gives us a connection between the entanglement structure and the field theory and the geometry. And so the first point I wanted to make is that it's really a lot of information about the geometry. So I would say that you can, using that formula, you could plausibly reconstruct the geometry from the entanglement entropies. And there's there's an asterisk. So clearly, if there's a part of the dual geometry where none of these entanglement surfaces probe. Okay, so say you have a field theory on a circle, and you look at all the extremal surfaces. Well, there could be a situation where there's a region in the geometry, in the middle of the geometry, where none of the extremal surfaces pass through. Okay. So if you took your CFT state, computed all the entanglement entropies, and then interpreted those as the areas of various extremal surfaces, well, you can't really possibly get any information about this region in the middle. Okay. So when I say you could plausibly reconstruct the geometry, what I mean is the part where these surfaces actually probe. So what I have in mind here is that you start with some state. Okay, so I hand you a state, which I guarantee is dual to some geometrical gravitational state. So there's some kind of classical space-time that is encoded here. And you want to figure out what is that space-time. So you take the state, and then you start calculating entanglement entropies. Okay, which in principle, knowledge of the CFT state should allow you to do. So we're just doing a field theory calculation. I mean, this is kind of an in-principle thing. So you're given this state. You can then try to calculate the entanglement entropies for all sorts of regions. Okay, so this one, this one, this one. So every region you pick gives you a number. In the end, you've figured out what this function is. This is a function from subsets of the space on which your field theory lives to the real numbers. And then the idea would be that you try to find a geometry M phi such that this geometry reproduces all those numbers. For all A. Okay, so since I've guaranteed that this is a holographic state, if you start with the right geometry, then you're going to get all the right answers. But the question is, well, would there be like a whole bunch of geometries that have the same answers for this, or is this constraining enough that it's going to nail down a geometry for you? Okay, and so the reason that I say it's plausible that it will nail down a geometry is precisely that this is way more information than just some metric functions that would specify a geometry. Okay, so the space of functions of subsets of the boundary is much, much larger than the space of metric functions that would describe a bulk geometry. So these ones, this would be a handful of functions of points, of the points describing your bulk, whereas this is a function of regions. So you're comparing.
You still have to argue that it's the right. You have the right information.
You would have to argue. Yeah, I mean, so this is an example where it's not always if there's a part of the geometry where that S of A doesn't tell you anything about, then you're not going to be able to reconstruct the metric. But so diagrammatically, so if this is asymptotically ADS metrics. Okay, and this is so this is supposed to look like a larger space. Functions S of A. Okay. Okay. So given one of these asymptotically ADS geometries, this Ryu-Takunagi formula will place you at some point in this space of functions S of A. Okay. And this set is way smaller than this one. And so, morally speaking, this problem here, it's like having 40 million equations for two unknowns. And so that's interesting because actually it tells you that so it's 40 million equations for two unknowns, and you're guaranteed that there's at least one solution. So it's not a proof that it's possible, but
is that
it's plausible.
Part of your definition of what you mean by being a holographic state?
Given holographic state means that there's an answer. There's at least one. And I want to figure what that is.
Is a criterion for when the dual would be a smooth geometry as opposed to something?
Yeah, I'm going to say a little bit more about that. Right. So I'll just mention that there are cases where this is a proven fact. So if you think about just two-dimensional spatial geometries. Okay. So there's a mathematical theorem So these are two-dimensional spatial geometries with a boundary. So there's a mathematical theorem that if I tell you, given any 2 points on the boundary, if I tell you the length of the shortest geodesic connecting those 2 points, and if every point in the space is touched by one or more of these geodesics, so there aren't any holes where none of the extremal curves pass, then you can actually, this is x bulk. Then you can actually reconstruct the metric. Okay. So this has been proven, but so it's a limited case, but I find it plausible that.
Sorry, does that assume that like through any given point there is only one geodesic that passes through there, even the two fixed endpoints?
I think what it assumes is just that there's no region in the geometry where no geodesics pass through. Okay.
And if it was a circle, every set of diametrically opposite points might.
Yeah. There could be lots of geodesics that pass through a given point. I mean, what you have to worry about is more that there aren't any, and then you don't get any. Then if there's a hole, then this doesn't give you any information about this.
But the other is no problem.
The other is fine. It's just like too much information. Yes.
Is asymptotically ADS given as an input when you start putting what?
Yes. Yes. So when I'm thinking about this, well, okay. So it's possible that some of this generalizes to other situations. What I have in mind when I'm discussing this would be that this space would be the set of asymptotically ADS metrics, and what we're trying to figure. So in general, oh yeah, okay. So by the way, this would be if you've never tried any of these holographic entanglement entropy calculations, this would be a useful thing to work out. It's starting with pure ADS space. So the claim over there. So the claim over there. Okay. So the exercise would be to start with pure ADS, look at a ball-shaped region on the boundary, and then try to find the extremal surface and compute its area. Okay, it's with some regularization. Okay, so yeah, this is pure ADS. In this is Pfefferman-Graham coordinates, and so a way to characterize the set of metrics that I'm talking about would be again to use this Pfefferman-Graham gauge. Okay, so you add on this metric. This function here is the thing that distinguishes various metrics from one another, and so it's really a question of can you figure out what this is given these extremal surface areas. Pardon? So in the bulk sense, so this boundary in these coordinates is z equals 0, and so your ADS space has an infinite distance to the boundary. Okay, so it's an infinite volume space, and what I want to do is just consider the region where z is greater than epsilon. Okay, so that's taking an infinite volume of ADS space, and then we're now cutting it off. So now it's a finite distance to the boundary. So it's an IR cutoff from the bulk perspective, and then famously, that corresponds to a UV cutoff from the field theory perspective. Okay, so yeah, following up on Oliver's point, if we look at this picture, okay, so these are classical geometries. These are the functions S of A. So these are basically potential entanglement structures. Not all of these are allowed. Not every function S of A is an allowed entanglement structure because you have constraints like strong subadditivity. Okay, so some of these functions tell you what the entanglement entropy would be for every possible region. Some of those points are going to violate entanglement inequalities. Okay. So there might be a part of this space which is ruled out. But the rest of them are allowed entanglement structures for field theory states. And entanglement structures that actually come from geometries are a very tiny subset of those. Okay, so only very special entanglement structures would be consistent with a geometrical Yeah, I'd love to be able to do that. Perhaps there's something that I'm trying to work on that I hope would connect with that. Yeah, well, okay, I could say a little bit about it. I think I'm going to talk in more detail about this in a future lecture, so I'll try to answer your question in detail. Yeah.
The space of functions SFA.
Yeah.
Is there a clever would I need all possible A's?
Yeah, that's a very good question. So, in general, if I want to know the entanglement entropy for this region, there's no way to get that by knowing the entanglement entropy for smaller regions. So I don't know of any useful way to reduce the amount of information that I would need if I'm talking about a general function. One of the points that I'll make later is that these entanglement structures that actually come from geometries, there is, in a way, a method. So that's a way to understand what these constraints look like. So let's say I just had the entanglement entropies for some special set of regions. So I'm going to choose ball-shaped regions. Okay. So if I have the entanglement entropies for ball-shaped regions, that turns out to be still enough information, in terms of counting how much information you have. That's about as much information as the set of metric functions. Okay, so when you see these very special entanglement structures, what it would be like is that there should be, in principle, some way of just using the entanglement entropies for regions of one particular shape and various sizes, and from that you could deduce, in principle, the entanglement entropies for all the possible shapes. Okay. Alternatively, and I'll probably talk about this more, if I just know the entanglement entropies for infinitesimal regions, okay. So if I happen to know the bulk equations of motion for this gravity theory that I'm trying to understand, then I could use the entanglement entropies just for infinitesimal regions to. Okay, so that allows me to understand the asymptotic behavior of the metric, okay, because these infinitesimal regions correspond to little surfaces that probe out near the boundary of the geometry. And then I can use the bulk equations to integrate in and find more of the geometry. And then I could use that geometry to calculate surfaces for larger regions and calculate those entanglement entropies. So another way to think about these constraints would be that there's a sense in which, for these holographic states, the entanglement entropies seem to be determined more or less by some local data. Okay. Yeah. It's okay. Yeah. So right. So what basically, if I think of a ball, that's characterized by a center point and a radius. Okay. And then a metric function would be some function of, so one of the metric components would be a function of the boundary coordinates and then the radial coordinate. Okay, so this is a function of sort of the same number of variables as a metric function. To get, and the metric functions, there's actually a set of functions which are related by some symmetry, some Lorentz transformations and things. So to get all of the metric functions, what you would need to do would be consider balls in various frames of reference. So it's actually independent information to calculate the entanglement entropy for a region in one spatial slice and another spatial slice. You get more information by looking at the different spatial slices. Okay. So any more questions about that? Okay, so I want to talk about another implication, which is at the start it's going to sound more qualitative, and then we'll try to make it more concrete by the end of the lecture. And so this goes back to this thermofield double story that I told you last time, where you have two CFTs and you put them in this special entangled state. And then Maldacena conjectured that this was dual to this two-sided maximally extended black hole geometry, where the geometry of a spatial slice looks like some wormhole connecting these two asymptotic regions. Okay. So there's an interesting point then if you just go and think about one CFT. Okay, so what I said last time was that apparently and magically entangling these two completely unrelated theories has created some connection between these two spacetimes, these two separate asymptotic regions. Okay. But going back to just a case of a single CFT, if we think about the vacuum state of a field theory, okay. Well, as we saw last time, or I guess as you saw more in Juan's lectures, there's a whole bunch of entanglement already in this vacuum state for a single CFT. Okay, so if I divide the CFT up into any two regions, then this one is heavily entangled with this one. I can do that in lots of different ways. Okay. And so given that the entanglement here connected up these two parts of the geometry, it's interesting to ask whether, is there a sense in which entanglement between A and A bar in the field theory is the thing that is responsible for having this connected space-time in the middle? Okay, there's all this entanglement in the field theory state in the vacuum of a single CFT. It's interesting to ask is that somehow what's responsible for actually having a nice connected classical space-time?
So if that were true, it would have to be true that you could only have quote-unquote lots of entanglement if the coupling is strong.
So, yeah, I mean, so far we're being qualitative. Eventually, we'll, so let me go back to here. I think it would be too naive to say that it's just the entanglement. So there's, I guess that's debatable. But I mean, what we'll see. So there's a very particular structure of entanglement here in this thermofield double state.
But I'm just saying if I took a free theory, right?
Yeah. So the entanglement structure would be quite different, and there's definitely entanglement, but the structure is different. And
When you say lot, sorry, maybe.
well, yeah. Here we're starting out very qualitative, and the point would be towards the end of the lecture we'll try to quantify all of this stuff. But if there were no entanglement, I mean, naively you might think, oh, it's the vacuum state. Maybe there's no entanglement, and then you would never think that entanglement had anything to do with geometry. But so yeah, I mean, all I'm saying is that at a qualitative level, in this situation, the only thing that relates these two CFTs is this particular entanglement that you've placed between the degrees.
Necessary, but not sufficient at all.
Yeah.
Okay.
Which I always am on that side of the necessary versus sufficient discussion, I think. I mean,
how could it? I don't need to belabor this, but
I think.
For a free theory, that it shouldn't have gravity field no matter how much entanglement.
Yeah, well, I mean, of course, I mean, it's probably still. I don't know if I would even be that quick because people talk about higher spin
But let's
theories.
talk about real greatest gravity. I mean, isn't that what you have in mind?
I do, yeah, and I'm certainly not saying anything about sufficiency.
Okay.
Yeah.
Just fine.
Okay. But yeah, people ask me every time. So actually, usually it's Steve Gettings that asks me that question. Did he just send you an email? No. Okay.
Actually, while we're
Yeah.
picking on you, I mean, this word "responsible for," is it, what is it? There's causation and correlation.
So
Is
yeah,
it
as
a measure of confidence or the
so I'm working towards a specific statement that, I mean, this is qualitative. It's going to motivate a bunch of things that I'll talk about, and then towards the end I'll make some specific statement that I think highlights the extent to which entanglement is responsible for or related to
Well, but it's not. That would mean it was.
yeah, no, that's too weak.
It's too strong. By the way, I'm not questioning the duality as Steve might be.
Yeah, no,
At all. I'm just saying
Yeah, no, I completely agree with you that yeah, there's some and it's related. I think we really only made the point here. Okay, so this is the same point, and I even underlined it. So I think this is some very special structure, and to really understand this, we need to understand these constraints. Yeah. Okay. Okay, so still at this extremely qualitative level, an observation that one could make is that if you started with the vacuum state and now just vary it, so consider a one-parameter family of states which still have some classical dual geometries, but where I decrease I start decreasing the entanglement between my arbitrarily chosen region A and this region A tilde, or A bar. Okay, so then according to Ryu Takenagi, what happens, for any choice, all I'm saying is that, well, I'm gonna decrease the entanglement. You could do that in any way that you want, as long as you're still within this set of holographic states. Okay, so within that set of holographic states, decreasing the entanglement, it decreases the area of that surface in the bulk, separating the two asymptotic regions. Okay, one can also argue that these two asymptotic regions are going to become farther apart, but I won't go into that. But again, so just at a very qualitative level, this suggests that there's some, that even though the boundary spacetime is fixed, when I do this decrease in entanglement, the bulk metric is going to change in such a way that, in a sense, it looks like the two sides are separating off from one another. Okay, so if I and I can imagine doing this, subdividing further and removing more and more entanglement. And at least within this class of holographic states, what seems to happen as I keep decreasing entanglement everywhere is that the whole thing just pinches off. And so going the other way, if I started with some state with very little entanglement, within this space of holographic states, I need to increase entanglement in order to get back to ADS. Yes.
So let's say we have some state and it doesn't have a classical holographic dual.
Yep.
We have an algorithm for trying to get an asymptotically ABS vector. So let's say okay, let's try to get a vector. Will it fail? Like, could we use this as a drive function?
Yeah, absolutely. So here's the potential algorithm that some people have used. Just pick a particular set of so choose these ball-shaped regions. Okay, so choose the ball. Let's take the ground state of I don't know, the Ising model or something. And so some or a free field theory. Okay, take the ground state, calculate the entanglement entropy just for these ball-shaped regions. Okay, and now ask, is there a metric that reproduces those entanglement entropies? And you haven't chosen too many regions, so now your problem is more like 10 equations and 10 unknowns, and you can find a solution. Okay, so you find a metric. Maybe you assume translation invariance or something, and then you're going to find an answer. Okay, and so you get like a potential metric that state could be dual to. Okay, but then how you would realize that this fails is that now you would, in the field theory, compute the entanglement entropy for some other region, and then you would check it against the holographic proposal, and you would find that it disagrees. Okay, so that's how you would tell that it wouldn't work. Yeah. 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 Sorry, I don't want to think about being in the space-time and doing some measures of modes. I mean, this is just here's the space of holographic states. Here's the vacuum. Here's a path away from the vacuum state where the entanglement entropy decreases. Well, surely there exist such states, but I'm imagining take a path through this space of states. Okay. Yeah. Okay. Yeah. So what I meant, what I was saying there, if there is an actual geometry that's dual your state, you'd really only need to look at a limited set of regions to deduce that geometry, okay? And then the fact that I've guaranteed for you that there is a holographic dual means that when you go and check the other regions, you'll find that they also agree, okay? But if you naively tried to use the balls to reconstruct a metric in a case where there wasn't really a gravity dual, you would still be able to do it because you've only chosen to look at a limited set of information, but you would find that the geometry does not correctly calculate any of the other entanglement entropies.
Would you expect that you would find that right away? Like one, other?
Yeah, I expect you would find that right away. You wouldn't have to work too. Yeah, I expect you would find it right away.
Just curious, would it still even be like, would it solve Einstein's equations, for example? Like, would it even be in space-time? So it's not the right space-time.
Well, you have to be careful because anything solves Einstein's equations as long as you have the right matter. So
would it violate some, like,
so if you start with you start with a physical field theory state and you calculate a limited set of entanglement entropies and you try to come up with a geometry. Yeah, I mean, I'm not. So I'm not sure if there's going to be something obviously wrong with it. Yeah. Yes. If the non-ball entanglements were only slightly wrong, then yeah, I mean, it could be a case. Yeah, maybe you're close to a holographic state. Okay. Yeah, these are all very good questions. I mean, I think it's happened various times. I mean, there are a bunch of papers where people try to do things like that, where you just start with you give some prescription that seems to generate a metric, starting with like an arbitrary field theory, and then it sounds like, oh, hey, holography is really general, and every field theory and every state has a dual metric. But I think you have to be careful to make sure that it's all consistent. That if you actually looked at enough quantities, you would find that it's actually really not being consistent with a gravity dual.
But then the Witten instanton problem, which is kind of space, can that be understood on purely topic grounds? So there are processes which I know.
Yeah, like well, I mean that sort of creates a hole in the middle of space-time. Is there an ADS version of that? There's not. There's not an ADS version of that, so I'm not sure if. So far, I mean, I think some of these lessons should carry over more generally, but so far we really understand things in the ADS case. Okay, so let me try to be more explicit. So I want to actually talk about exactly what does the entanglement look like in the case of the vacuum of a CFT, and how does that compare with, say, the structure of anti-de Sitter space? Okay, so just to make things a little bit more concrete, so I'm going to consider a conformal field theory on a holographic conformal field theory on a sphere in the vacuum state. And so this is dual to pure global ADS. Okay. Okay, so hopefully you've seen this represented as a cylinder. This is time. So the boundary is a sphere. I've drawn it as a one sphere. But in general, this is representing some d-dimensional sphere. And then this bulk spatial slice has the geometry of hyperbolic space, of d plus one-dimensional hyperbolic space. Okay, so I want to consider a ball-shaped region Okay, so well, here's the sphere. I want to consider a ball-shaped region of the sphere. Okay, so I'm just basically dividing my field theory space into two parts, and here's the part A, and then there's the complementary part A tilde. Actually, I think let me draw it as if those are of equivalent size, but I want to really be considering the general case where this is one part of the ball, and then there's the complement of the ball. Of this one part of the sphere and the complement. Okay, so A. Okay, so I'm interested in, okay, so what is the so at last time, what I said was that we can represent the state, this vacuum state, as some kind of entangled state. So I said that we can actually think about, I introduced this domain of dependence region. Okay, so here's the domain of dependence of that ball-shaped region. This is on the boundary geometry. And then this is the domain of dependence. The other part, and what I said last time is that the CFT on this domain of dependence region, this causal diamond, is in a sense, you could almost think of it as an independent theory. Okay, so in this way of looking at it, we really have a CFT on DA and a CFT on this D bar, or DA bar. And so we should be able to represent the vacuum state of the CFT on the sphere as some entangled state between those two theories. Okay. And it turns out we could do that very explicitly. And the way that we do that is to use a conformal transformation. Okay. So there's a conformal transformation that maps a particular region. Okay, so I'm going to draw it over here. It's easier to draw this way. So there's this diamond-shaped region on the cylinder. And there's some conformal transformation that maps that diamond-shaped region to Minkowski space. Okay. So that's the kind of thing I'm talking about. So we're imagining now the diamond-shaped region is a little bit hard to draw, but it's okay. So this point here is going to be this point here, and then there'll be that's difficult to see. So I want to rotate that. So here's the diamond-shaped region that gets mapped to Minkowski space, and here's my dA, and then on the back side there's the dA bar. Okay.
This is just the usual funny gray path.
This is, yeah, inside is the Poincaré patch. Right now I'm just thinking about the field theory on the boundary. And so there's a particular, if I unfolded this cylinder, which I should have done to start with, then there's a diamond-shaped region that maps by a conformal transformation to Minkowski space, and these two, what I've defined are these two regions, dA and dA bar. Okay, and so this maps to Minkowski space, and those two diamonds, it turns out, map to the these complementary wedges. So these are usually called the Rindler wedges. Okay, so I've put these hats because these are the regions that the domains of dependence map to. Okay, so we started out with our CFT on the sphere. And then we said that this particular region of the sphere times time through a conformal transformation gets mapped to Minkowski space. Okay, and so that mapping induces some mapping for states. So if I have any state of the CFT on the sphere, there's some corresponding state of this CFT on Minkowski space. Okay, and for the particular case of the vacuum state, that just maps to the vacuum state of the CFT on Minkowski space. Okay. Okay, so our question was to understand the representation of this ground state of the CFT on the sphere. We want to understand that as some kind of entangled state between these two sides. Okay. And what we've done by this conformal transformation is to translate that to the question of how do you represent the vacuum state of Minkowski space as some kind of entangled state between the field theory on the left side and the field theory on the right side. Okay. And that's a very well-known result. Okay. So actually, for any quantum field theory, it doesn't have to be a conformal field theory. There is a result for the density matrix for the half space. Okay, so I think Juan wrote this down. I'll write it down again. I'll try to explain it a little bit. If anyone wants, so this is something that can be derived without too many steps using a path integral method. That would be something I could possibly discuss in the discussion section if people are interested. But for now, I'm just going to state the result and kind of explain what it means. Okay. So here we are. So here's our Rindler wedge of Minkowski space. Okay. So there's a particular time-like coordinate that you could define called eta. And what this is just the flows along eta are the things generated by the boost generator in Minkowski space. Okay, so H eta is the quantum operator associated with the translations in eta. Okay, that's the same thing as the boost generator. And you could also think of it as, so these are trajectories for accelerated observers. Okay. So you could also think of this h as being something like a Hamiltonian for accelerated observers. Okay. So this density matrix, so that's this operator. So the usual Hamiltonian operator is the thing that generates the ordinary time translations. This operator is just the thing that generates some other kind of time translations, okay, which are also symmetries. So explicitly, like classically, okay. So classically, this is the operator that generates these coordinate transforms. Okay, so this form indicates that the density matrix is, we would say it's thermal with respect to this Hamiltonian. Okay, so that may not totally be obvious. So, in general, if I have a Hamiltonian, I could write it explicitly as like this, right? Because then you can check that these energy eigenstates are eigenstates. So you act without an energy eigenstate, you get back this energy eigenvalue. Okay. If I want to write down a thermal state, then we'd say that it's 1 over z sum over I of e to the minus beta ei. So this is the thermal density matrix that we talked about last time. Okay. And then you'll notice that if I actually look at the structure of this state, it's actually the same thing as writing down e to the minus beta h. Okay, so it's just a trick. When you exponentiate that, because it's diagonal, you just end up with that. Okay. So if I wanted to write down, in general, what is the thermal density matrix, you might first think of this. That's just the states with the Boltzmann weights, but you actually write it in this convenient form as just the exponential of the Hamiltonian. Probably most of you have seen that. And so what we're saying is that this density matrix for the right half Rindler wedge is actually of this form, but it's not the usual Hamiltonian, it's this Rindler Hamiltonian. Okay. And so this is directly related to the statement of Unruh that accelerated observers in the vacuum of Minkowski space will experience thermal physics. That if they have a particle detector, they'll measure some kind of thermal spectrum of particles. Okay. Good. Okay. So that was for the right wedge. The left wedge is also thermal. And so this should be starting to sound like the situation that we had when we were talking about the eternal black hole. Okay, so we have two systems. They're both in a thermal state. And then we can ask, well, what is the full state? And the answer is that, again, it's exactly this thermofield double type of state. This sum really should be an integral. Okay, but yeah, basically it's the same state as we had that we said was dual to the black hole. Okay, there's actually a way to understand this that makes it sound even closer to that thermal field double state that described the eternal black hole, and that is that you could by a different conformal transformation. Okay, so instead of doing this one, there's a conformal transformation that takes dA, so this domain of dependence region, to hyperbolic space times time. So just to some static hyperbolic space. And similarly, dA bar maps to some hyperbolic space times time. Okay, and so in that picture, you've mapped dA and dA bar to just this pair of CFTs on two hyperbolic spaces. Okay, and then the vacuum state of Minkowski space maps to like exactly the thermofield double state, where it's just the thermal state of the CFT on hyperbolic space with the ordinary Hamiltonian. And so it's exactly the same thing as the thing that was dual to the eternal black hole, except we've replaced the sphere by hyperbolic space. Okay. All right. Okay, so this is it. So we get this entangled state of left and right. Okay. And so this makes things a little bit more explicit. So you know, we understood this vacuum state of the CFT. We divided it up into two regions. Before we kind of said, oh yeah, they're going to be entangled. There's some way of representing that state as an entangled state. But in fact, it's precisely the same kind of entangled state as we had in describing the thermofield double. Okay, so it's not just that there's entanglement. There's this very particular structure of entanglement where when I divide it up in any way, I actually get this kind of thermofield double form. And so that makes it a little bit more plausible that the same thing is going on here when describing pure ADS that was going on in the thermofield double when we saw that connection between the two halves of the spacetime. Okay. So yeah, so let me I'll just draw the two pictures. Okay. Yeah, so in one case we had a CFT on a sphere and another CFT on a sphere, and this was the structure. And now we've got we've chosen some region of the boundary of ADS and some complementary region, and we've seen that the vacuum state can be expressed as an entangled state. And you have these two density matrices, row right and row left, that have a thermal interpretation. Okay, so now I want to ask the following question. So this is a question that came up in the discussion of the black hole. So we originally stated that the thermal state of a CFT is dual to the black hole, and then I said, well, what part of the black hole is it dual to? What does the density matrix rho actually describe? Is it this region outside the horizon, or does it include some stuff behind the horizon, or is it the whole thing? I want to ask the same question in this context, which is a little bit more. I mean, we're just talking about pure ADS, so it sounds more pedestrian and straightforward. So hopefully we can get some insight. Okay, so what info about the geometry is contained in row left and row right? Okay. Okay, so as with the black hole, the full entangled state should encode the full space-time geometry. Same thing here. If we know this full entangled state, that's equivalent to knowing that we're in the vacuum of the CFT on the sphere, and so that allows us to get reconstruct the entire space. But if we only know the density matrix for one side, then what do we get? Okay, and there's actually a very plausible answer here. So Okay, so the plausible answer is that that the density matrix rho right knows about this, what I'll call the Rindler wedge of ADS. Okay, so over here we were talking about Rindler wedges in the boundary spacetime. Now what I'm saying is that there's a particular region of ADS, which you can define in various ways. So one way to define it is that if you look at that domain of dependence region D, this causal diamond on the boundary, this Rindler wedge is the intersection of the future of that region with the past of that region. Okay, it's all of the points in the bulk where you could, from this region on the boundary, send in a signal and then receive a signal back. Okay. Alternatively, it's also the region of the bulk that would be accessible to some particular accelerated observer that starts here and ends here. So you could think of it in various ways. Okay, so I'll try to make it plausible that knowing the density matrix for rho allows you to understand the physics in that region, but not anything beyond that region. Okay, so what could you do given the density matrix rho for this right half region? Well, you could calculate any field theory operator. Or any field theory quantity which is restricted to this diamond region dA. Okay, so if I just know that I have this density matrix, I could compute correlation functions in that region. I could compute entanglement entropies in that region. So I could compute all sorts of things, and many of these things have holographic interpretations, right? So for example, I could compute, so one thing that makes this particularly plausible is imagining a response function. So say I perturb the field theory here, and I look at the response here. Okay, I look at the response there. That type of, so people have discussed this type of function in ADS CFT. This type of function can be very sensitive to changes. So if I made a small change at a point here, so let's just think physically. Say someone puts a little mirror in the bulk at some local point that happens to lie within this wedge. Okay, so I put a little mirror here. Well, if I were to send a signal in from the boundary and then measure what the effect is here. If I have the mirror there, well, the light could I could just set it up so that it bounces right back, and I'd see a big effect. Whereas if the mirror weren't there, it would be completely different. So response functions like that could be very sensitive to local bulk physics within this wedge. Alternatively, you could just think about calculating entanglement entropies, and that so I choose a space-like region in this region dA, and then I calculate the entanglement entropy, and that should tell me the length of the area of the surface bounded there. And it's not hard to see. So this is the Ryutaki-Nagi surface that calculates the entanglement entropy of the entire state. But then there's all sorts of other smaller regions within A. And it's not hard to see that this wedge is filled out by entanglement surfaces. Okay, so if I calculate all the entanglement entropies for this state, I kind of get information about all parts of this wedge, but nothing outside it. Okay. Okay, so I'll just say.
When you say nothing outside it, do you more precisely mean if you set something in from the left, so you have that left side, that you wouldn't be able to.
Yeah, let me. That's the next point. So, what I mean about nothing outside it is the following. So, So we're fairly convinced that you can learn about what's in here, but then we can ask, given row R, could we actually learn about anything? Could we deduce the geometry outside there?
There are two cases to consider.
Okay.
Whether you have the left, like you've drawn it, and then more the left. Then first is just talking about stuff that can be sourced from the right, and just but still following it through to the middle. Those are two different classes.
Well,
Try to describe in the middle region, and the stuff on the left is really hard to just copy.
so what?
Everything that came in from the right.
But I mean, if there's stuff coming in from the left, whatever you send in from the right would potentially interact with that, right? So it seems like I'm not sure the distinction. So if I have something falling through this surface, then as soon as they fall through there, I need to know whether there's something.
What I'm saying is that if nothing can come in from the left, everything is determined by the initial state on the right, like in a one.
Oh yeah, but here, okay. So here the context is. What I'm imagining is that instead of someone telling me the entire state of the CFT, all they tell me is that the density matrix for the right-hand side is this. And then I want to say, what could you definitely deduce about the dual geometry? So I'm not making any assumptions about what might or might not be coming in from the left. And in fact, so let's say I take this CFT vacuum state, for which you just keep going and there's ADS all the way through. And then imagine acting with some operator. So I want to consider another state, or just act with this operator. It's a unitary that acts on the left side but doesn't do anything to the right side. Okay. So this kind of state, this kind of state will have the same density matrix as for the vacuum state. Okay. Because I've only, if I've only affected this, and because it's a unitary, if I go and calculate the right-hand density matrix, I find exactly the same thing as before. Okay. So this is the same row R, but row L will be changed. Okay. So that means and there's all sorts of U's I could choose. But these include things where I make some kind of perturbation anywhere I want on this dA bar region. Okay. So within the class of states that have this as the right-hand density matrix, there are plenty of states. There are states where I have perturbations at arbitrarily early times in this diamond. And then those will propagate and change the physics beyond this surface. Okay. Or similarly, you could imagine perturbations that affect anywhere outside this region. And so, right. So the point is that the effects of this CFT perturbation in L can affect anywhere outside the wedge. Right. Yeah. Oh, yeah. Good. Yeah, I may want to. Okay, let me just explain that point. But yeah, let me do that. So yeah, okay. Let me try to finish here. Unfortunately, okay, this will be a little bit quick. Okay, let me quickly try to summarize this. Okay. Okay, so the conclusion of this thing was that if I have the density matrix rho R, then what my conclusion was is that this described the region in this right-hand Rindler ADS wedge. And it doesn't have information about the rest because there are lots of states with the same density matrix where what happens past that place will differ. Okay. So if I want to know the rest of the geometry, I have to know the full state. Okay. So this. So knowing the full entangled state, like in that black hole geometry, okay, sort of tells us what happens in the rest of the geometry. But the details outside the wedge depend on the purification. Okay. And then finally, I was going to talk about, so rho R is this ensemble okay, so we could think of this ensemble of eigenstates of this Hamiltonian that, it was the Rindler Hamiltonian. In the black hole context, it was also interesting to think about these energy eigenstates. So where you take instead of the entire ensemble, you just choose one particular pure state. Okay, so you remove, that's like removing, in this context, removing the entanglement between the left and the right. Okay. And so what would happen is that, like in the black hole context, we had this discussion where most observables, if you calculate them for this typical state in this ensemble, they're going to give you the same answers as this density matrix. Okay, so if I were to just replace the density matrix by a pure state, I don't expect that to change the geometry in the wedge. Okay. However, if you look at the entanglement between the left and the right, it just goes to 0. So that's suggesting that this, so previously when we had this nice full geometrical space-time and we had a particular area of this extremal surface that corresponded to the entanglement entropy, if I take Ryu-Takeyanagi literally, then what happens if I remove all of the entanglement between left and right, I replace this entangled state by, say, a product state. Ryu-Takeyanagi would tell me that the area of this surface just goes to 0. Okay, so it sounds like what's happening is that when I go just to the pure state, it sounds like what's happening is that something is, instead of having this dotted line being some well-defined geometrical thing, something singular is starting to happen there. Okay, so it's suggestive that this is maybe dual to something that looks like, has the same exterior region, but it looks like that there's a singularity now on the edge. Okay. So in that case, what I would get if I replaced the entangled state of the two sides with just the product state of the two sides, it would be like going from this nice ADS space to a space where, it's going from this nice ADS space to a space where I just have the two wedges, okay, and then nothing else outside. Okay, so you could say that, this, in general, you have row left having this information, row right having this information, and then the information up here is encoded in, precisely how are these two sides entangled. If I remove that, then the implication, just like in the two CFTs on the sphere, is that you would just have basically two separate spacetimes. Okay. And then the final thing I wanted to say is, all right. So now okay. So now, okay. So let me get back to the original point. I mean, now there's a fairly precise statement I can make, which is, imagine choosing any point in ADS. So choose any point in ADS, and choose some surface that passes through. So here's a point, here's a surface. Okay, so that surface would be part of some extremal surface that ends on the boundary. Okay, that divides. So that divides the boundary into these two regions, A and A bar. Okay. All right, so for any point and any plane passing through, any space-like plane passing through, there's actually a natural division of degrees of freedom on the boundary. Okay, and then in terms of those two regions, the vacuum state of the CFT is precisely this kind of thermofield double entangled state for those two regions. Okay, and specifically, if I tried to then take those two regions and disentangle them in as mild a way as possible, so that I preserve as much of the physics as possible. What I would end up with would be just these two kind of disconnected regions. And so there's a sense in which we've now understood, given any point in ADS and given any plane, we can identify particular subsets of degrees of freedom in the boundary, where if I removed the entanglement between those degrees of freedom, that would basically cut the space, disconnect the space precisely at that point. Okay, so I can sort of be specific and say, well, I would say that the fact that I can go from here to here in a smooth way, I can now point to some particular, well, that relied on the fact that subset A and subset A bar of degrees of freedom were entangled in this thermofield double type of way. Okay, so that's kind of the precise statement that I would make it about ADS. That's all.
There's a lot of questions, but people also want to get coffee out. Actually, was your question about entanglement, is that ever answered?
No, and I'd really like to answer that. Okay, yeah, I'd really like to answer that. Okay. Okay, so I asked the question, what is the dual of rho? And that was in the context of ADS. But a few years ago, we wrote a paper considering this question more generally. So given any kind of holographic state in some CFT on a boundary space, and given any spatial region A, okay, so here's the full state, and I know that it's dual to some geometry M. So the question is, if someone just gave me rho A, how much of M could I actually figure out just by knowing rho A? Okay, and so over here I gave two possible answers. So one of them was, so first we think about this domain of dependence region of A. That's the region where any field theory observable localized in that region, I can calculate if I just know rho A. Okay, so I can get anything in that region. And so I talked about two different kinds of things over here. And one of them was kind of causal things, where I looked at response functions, and that roughly corresponded to sending a signal into the bulk and receiving it back. And there's a natural region then associated with with those things, and that's the intersection of the causal future of dA and the causal past of dA. So that's some particular wedge of the bulk, which is often called the causal wedge. Okay, but what we what we suggested was that there's actually a larger wedge that you could reconstruct. And that comes from looking at these other quantities. So computing entanglement entropies for subsystems of A. Okay, and then you can, those correspond to the areas of extremal surfaces. And it turns out that, so if you define something else called the entanglement wedge, I think we didn't call it that, but later people have called it that. We call it W. So actually, it was like W hat or tilde. I don't know. Okay, so these surfaces fill out some particular wedge. So you look at any spatial region within dA, and then you look at the extremal surface from that region, and then that fills all this union of all those extremal surfaces fill out some region in the bulk. Okay, and so that is generally larger than the causal region. Okay, so if I have ADS, but now there's some matter inside, there's a famous result of Wald and Gao that says that a light ray going through the middle of ADS actually takes longer than a light ray going around the boundary. Okay, and so you can use, based on that, you can argue that, so say you have a star or something in the middle of ADS, you can argue that the causal, okay, so if I divide the space into two, the causal wedge associated with one side, it actually doesn't go all the way to the middle. Okay, if it did, then it would be the same amount of time for the light ray going through the middle of ADS as going around the outside of ADS. Okay, and so the two, according to the causal wedge proposal, knowing those two density matrices, it would only tell you about this wedge, and then there'd be this whole region in the middle where you wouldn't have any information about. So what I found to be more plausible, I mean, given that, given that the density matrix rho A and rho A bar, in particular, they have the information about the entanglement entropy of A, which is equal to the entanglement entropy of A bar, which is equal to the area of this surface that goes right through the middle. So it's a bit weird to say that you don't have that information given those density matrices. And so, yeah, so what I find somewhat more plausible is that actually knowing these two density matrices, or knowing the density matrix, would actually allow you to deduce the geometry everywhere inside that entanglement wedge. Okay, so that terminology comes up in various papers now. I think causal wedge and entanglement wedge are the standard things describing these two. Okay.
Yeah,
I maybe.
There's this really simple point here that should be brought in.
Okay, all right, sure.
Which is just, you said this thing about how the middle is all about entanglement, right? Now consider the one side of the which is the hyperbolic threshold down to the form, which means go out on the coulomb there. So take the Poincare pattern. Just go out on the coulomb. Okay. So then what happens is that this is a layer.